Hello, everyone. My name is Julie Payette. I'm the Governor General of Canada. We are on October 8th, 2020, again, in the middle of this pandemic, second wave. Science has been at the forefront of almost all of our conversation. We are hoping for solutions to get us out of this terrible health ordeal that we are all living throughout the planet. But today we thought we would ask about the significance of science and why it is so important to keep searching in every corner and asking ourselves questions. And for that, we are absolutely honored to be joined by an extraordinary person, one of the greatest researchers of our country and on the planet. And I'm welcoming Dr. Victoria Caspi, professor of physics at McGill. I think she's got my dream job, at least my second dream job after another, and she's the director of the McGill Space Institute. She has a PhD in physics from Princeton University, and she specializes in research on neutron stars and pulsars, and she'll tell us about this a little bit. One of the many achievements that she's done is that she's discovered celestial bodies that do things that we did not know could exist, like spinning 716 times per second, like a pulsar, and other that are called magnetars. Maybe she'll tell us about that too. She's a companion of the Order of Canada, rightly so. She's the first female scientist to win the Gerhard Hertzberg Gold Medal of Science in Canada, and she won that in 2016. I was there when she was awarded it, and I cannot tell you how proud I was. Because we go back a long time, we're both mothers of young people and lovers of science. Even though I've introduced her as Dr. Victoria Caspi, she's a longtime friend. So Vicky, welcome to the GG Conversation. Hello.
Thank you so much, Your Excellency. I'm really honored to be here.
So tell us, as I mentioned, science is at the forefront right now. It's credible, it's trusted, people are counting on it. Why is science so important in our society, and why do we forget it sometimes?
Yes, well, science, sometimes things like astrophysics or astronomy can seem, why is this relevant? Why is it important to look up at the stars when we have so many problems here on Earth? But I think it's very important to remember, first, of course, it's inspiring, and we do sometimes need inspiration from somewhere. But more practically speaking, the sorts of technologies and innovation that's driven by asking questions that are at the forefront of knowledge translate to so many benefits for society that just are incredibly useful. So, for example, in developing different types of imaging, we can create CCDs that can make cameras that can take images in very low light, or we can use algorithms that computers use for MRI machines for medicine that were developed for combining signals from different types of radio telescopes. There's a million different applications of astronomy to society, and it's all driven by asking those kind of bizarre, extreme questions about the universe. How do you solve some of the toughest problems in the universe? Well, you need technology, and you need unusual technology then you develop, which turns out to have fantastic purposes here on Earth.
They sure do, and it's an age-old question. Since the dawn of time, people have looked up to the sky and wonder, what is this that brittles? What are these stars? We call them stars. And by the way, when you look at your profession, an astrophysicist, astro means star, and physics is basically a Greek word for nature. You're someone who looks into the nature of stars. And we have scientists that look into the nature of genome, or the nature of molecules. And that knowledge always translates. The thing, though, is we never know how it's going to translate exactly, and we need to keep on searching because we can't tell where the next discovery is going to come. So when you look at the stars, you ask yourself the question, what is this? Who are we? What are we part of? And it is kind of important and fundamental to figure this out, because it is we live in an extraordinary world, and we need to understand what it is. So by looking out, we discover actually that there's a lot more than what we can see with the naked eye, can they?
Yes, absolutely. I mean, first of all, the naked eye, we see all sorts of things, but it's only one tiny portion of the full spectrum of light that's out there that includes radial light and infrared and all the way up to ultraviolet and X-rays and gamma rays. And the universe and stars, they don't really know too much about the human eyeball physiology. They produce light across the full spectrum. And in each different wavelength regime, each different type of light teaches us something different about the universe. So what's apparent to a human eye, which is actually not particularly sensitive, to the objects way out on the distant reaches of the universe, is just a tiny sliver of what's actually going on out there. And once you start looking with telescopes using technology, boy, there's quite a story going on out there.
So now it's mind-boggling. We know, so it is true. When we look out, especially with a telescope far away, we look back in the past, correct?
Yes, absolutely.
And we never see the exact present and definitely not see the future. However, that is telling us a number of things about how celestial bodies evolve because they're not static. They are born and they die. Can you explain a little bit more about this?
Yeah,
Like
certainly.
our sun.
So light travels, as you say, at a finite speed. And so the further something is away, the light must have originated earlier. So you're seeing earlier in the history of the universe. In our galaxy or in our solar system, this effect it's not a big effect. The sun is only about 8 light minutes from us. So we're looking at the sun as it was 8 minutes ago. But when you start looking beyond our galaxy and you look to the distant reaches of the universe, you're looking back millions to billions of years. And on billions of years, now you're looking into the earliest times of the universe. So using very large telescopes, we can see galaxies and stars as they were forming very early on in the universe. And this teaches us about where the universe came from, how structures like galaxies and stars formed to eventually be able to form the sorts of planets that we think we need for life.
It's interesting. We get questions from the public, and we got some in advance of our conversation. People are very interested in this because it is fascinating, and I will take advantage to salute the people who are listening to us live on YouTube and Facebook. Thank you for being there. I'd like to put a question there because when you say we look back at the very beginning of the universe, which is how many billions years old?
Oh, the latest number, somewhere between, around 14 billion, something like that.
14 billion years old, the Big Bang, the universe, what we can see. And there was a discovery a few years ago of what we call gravitational waves. And I know that all of us who are very connected to science and definitely in your field, we were very excited when we had proof that there was such thing. That's the ripple that happened at the very beginning of the universe. And we were excited about it because it was a proof of a long understood theory, but it had never been seen. And we have Steve Monroe from Regina, who is asking a question about those gravitational waves. He's asking if that discovery, how many have there been? Have we seen many times the gravitational waves or just one time? And have they been linked to a particular stellar event?
Right. So first of all, there's theories. There's different types of gravitational waves. There are some that are theorized to originate in the early universe at the time of the Big Bang. But the ones that have the gravitational waves that have been detected directly using gravitational wave detectors here on Earth, those are detecting gravitational waves from massive objects that are colliding. So to answer the question,
a long time ago.
Yes, a long time ago, yes. But these are stellar mass type objects, meaning 2 black holes, for example, or a neutron star colliding with the black hole. we are detecting the very end of the approach of these two stars to each other. So when stars orbit each other, binary stars, when they orbit each other, eventually they will collide. And it's that collision that produces a huge burst of these ripples, as you say, of gravitational waves. And so what we have detected using gravitational wave detectors is about 15, certainly that's about roughly how many have been reported, about 15 collisions, mostly of two black holes with each other, something that we have absolutely no other way of detecting. Black holes produce no light. But when they collide, they produce these ripples in space-time that we can then detect as gravitational waves. So this question is very timely. A whole new window in the universe is being opened through gravitational wave detection.
And what it tells us is that the calculations that we've made on Earth on a theory, when it proves true in the nature, when we get to have evidence of that through our telescope and our instrument, it reinforces the fact that you can theorize, you can think out physics, even if the evidence is not exactly quite there, because you see where there's something missing, that there's a gap there that doesn't fit the current theory. So that means there's something else there. And that's when you go looking for. And I believe that right now, often we say that one of the greatest or most fundamental questions in physics right now is what is this universe made of? Is it made of galaxies and planets and moons and pulsars and neutron stars, black holes, or is it made of something else? And I understand we think it is made of something else, dark matter, dark energy. What is that?
Oh, yes. Well, so dark matter and dark energy are two different things. And both are descriptions really of our ignorance, in the sense that, for example, dark matter, we infer its existence from motions of stars and gas and galaxies, where the motion is not as we expect given the light that we observe. So, for example, in spiral galaxies, we see that on the outskirts.
And we're in a spiral galaxy ourselves, right? In the
Yes, absolutely. The Milky Way galaxy, our galaxy, is a spiral galaxy. And in galaxies, including the Milky Way, but in all types of galaxies, we see that the motions, especially on the outskirts, are way too fast to be explained. And that means stars are actually rotating around the galaxy way too fast to be explained by the matter within that we can see within the galaxy.
So there must be something else.
There must be something else. We also see evidence for it in clusters of galaxies. If you look out with big telescopes, you can see that galaxies like to be with their friends, with other galaxies, just like people. But they're buzzing around inside clusters of galaxies way too fast to be explained by the light that we can see from those galaxies. So there's many different lines of evidence for the existence of some sort of matter that we simply cannot see. And that's what we refer to as dark matter. Now, you also mentioned dark energy, and that's different. Dark energy is what we call the apparent force that seems to be accelerating the expansion of the universe.
As all the matter we see from our telescope is moving apart.
It is moving apart on larger scales, not within our galaxy. So, or your hand is not expanding, and the galaxy is not expanding. But if you go to further distances, then yes, you start to see that actually all galaxies are moving away from each other. And this is one of the lines of evidence for the Big Bang, that the universe was created in a large explosion. But you might expect, you have an explosion, the matter flies apart. You might expect eventually gravity to pull it back in, or you might expect it to coast. But instead, to our shock, the universe expansion is getting faster. And that was a real surprise, and we do not understand why. And we refer to whatever is causing that accelerated expansion as dark energy.
You know, I'm going back to the idea that, you know, science, you always need a certain percentage of people who will be looking at the unknown and trying to discover and understand what we don't understand. I mean, we've seen, for example, lightning and what it does for age old again, but the day we started really investigating what the phenomenon was and investigating the way the molecules are formed and the atom and discover electron and electricity, then it completely transformed our world. We don't know what that matter is. We don't know what that energy is. And do we understand gravity really? We can describe it well, but do we understand how it works? Why is it that the moon stays close to the earth and doesn't go away? Like in science fiction.
You're asking a fantastic question. Certainly, we understand mathematically, how gravity works. We understand that mass attracts other mass, and we understand, even in Einstein's theories, how actually, if you consider, the theory of general relativity, what mass is really doing is deforming space and time, so that the moon's orbit is forced upon it just by the nature of the shape of space around the massive Earth. Now, those sorts of that theory and that mathematics, this was all proposed by Einstein. And then, just to circle back to what we were talking about earlier, one of his predictions in describing gravity as this, distortion of geometry, was the existence of gravitational waves, which was then, just in the past few years, experimentally verified. So we understand a lot about gravity in these sorts of regimes. The place where gravity is still mysterious to us is in the particle level. So exactly how is the force of gravity transmitted between objects? Is there a particle called a graviton? In the same way that the other forces are all mediated, the other forces all have particles associated so that objects to talk to each other. So
yes, two electrons who repulse each other, and particles, and same with magnetic force, the north and south of a magnet. But in the case of gravity, which is, oh, by the way, the force that is probably the most dominant force right here on Earth, it directs everything and forces us to have our feet well planted on the. And we don't understand what it is that connects that.
Right. So the unification of gravity with the other forces, how they can be combined, using particles as mediators, as the ways they can communicate. How does the Earth know that you're there to pull it down? That is not well understood. But there's people working on it. There are people working on that.
Right, and gravity affects us. So this is something that the more we discover about it, the more maybe we can make use of it, and make use of it in a way that we can't even imagine. We've touched on dark matter and dark energy, that we had several questions. Don Garbutt from Toronto was asking about how they were related. He also asked about, what are WIMPzillas? What are that?
Well, so WIMPzillas are evidence that physicists are creative when it comes to naming things. I think that's a
yeah, I would suspect.
Well, so first, what WIMPzilla? So a WIMP, in physics speak, is a weakly interacting massive particle. It's the opposite of a macho, which is a massive, compact halo object. Both of these were theorized to explain dark matter, in fact. So dark matter could, when you see stars moving too fast in a galaxy, you might think, well, perhaps the dark matter could consist of other massive kind of objects, like black neutron stars. And so those were referred to as machos, as potentially explaining dark matter. That has been largely ruled out through all sorts of observations. And the alternative are WIMPs, these particles that are difficult to detect in any other way. So they're weakly interacting, but still they're particles that perhaps could make up dark matter. So the WIMPzilla is a particularly massive WIMP that's hypothesized, has not been detected or verified. It's one of many, many different theories for a particulate nature of dark matter.
it is difficult to comprehend, I must say. I remember studying physics and the first time introduced to the law of relativity. Uh, it 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 seems like it's difficult, but actually it is something that happens all the time, right? We do now. Anybody with a telescope or somebody who's a part of a astronomy club or studies astrophysics with you has an opportunity to see things with their naked eye through the telescope that tells us that there's so much happening out there. We have one of our colleagues at the Governor General Office, Chris Grinham, who says, you know, what happens when a star collapses? Because that's another question. You know, where are we going to go? We know our sun's going to burn thermodynamically for a long, long time, 5 billion years. So we'll be long gone, but it will one day not burn anymore. What do we know about that? And what dictates that a star collapse? And what makes it turn into a pulsar, or a magnetar, or a black hole?
Ah,
If
yes.
indeed.
So, one thing in astronomy, before you were asking me about about dark matter and dark energy, and those are topics where we're still learning and we don't understand, and we're happy to say we don't understand, and we're working on it. Stellar evolution, the life cycles of stars, that's actually very well understood. That is an area of astronomy that is on very solid ground, and we know exactly what will happen to the sun. The sun is a average mass star. It's
Not so
typical.
big, not so small.
We love it. We love it.
Middle ground star. There you go.
That's right. And those types of stars, as you say, it will burn for another several billion years, on the order of something like 5 billion years. But then eventually it will run out of its nuclear fuel at the center, and it's not massive enough to ignite and burn other nuclear fuel. So it can burn hydrogen. It can fuse hydrogen into helium. But once it's done that, I'm speaking I'm simplifying slightly. Then it can't continue to shine in the way that it does now, and it will collapse. Basically, stars, any star that you see, is a delicate balance between the inward crushing pull of gravity, which is relentless, never stopping, and the outward balance of gas pressure, that's hot gas pressure that is heated by the nuclear fusion at the core. And when the core turns off, as it inevitably will, then gravity wins, and it will collapse into an object that we call a white dwarf. White dwarfs are then supported by a quantum degeneracy pressure, and we observe this. It sounds a little far out, but we observe thousands and thousands of white dwarfs in our galaxy, and they essentially live forever.
And if I say, you know, the study of that alone is perhaps one of the ways that we can eventually, hopefully, solve our energy problem, because the sun is a thermonuclear reactor, like you mentioned. It's doing fusion.
Yes.
And currently, we are not able to
Yes.
do that kind of thing unless we do it under a very controlled laboratory. We can't use this, but we know about nuclear fission, but that creates radioactive material. So we don't like this as much, even though we can do it very safely. So right now, there's a lot of effort, I believe, throughout the planet, and our reactors are being constructed so that we can understand that. That too might be completely revolutionary the day we understand how to produce fusion on Earth.
Absolutely. It's something the sun does routinely every single day, and it's done it for billions of years, and yet we haven't figured out how to do it practically, given the constraints.
Now, you didn't tell us about a pulsar. I know that's your field of expertise. Give us a definition of what is a pulsar. Can we see a pulsar through a telescope?
Actually, so in optical light, they tend to be very faint. And so what these are collapsed remnants of very massive stars. So not like the sun. The sun will turn into one of these white dwarf stars, but a much more massive star, like something that's 10 times the mass of the sun, will eventually collapse into a neutron star, which is, and some neutron stars are pulsars. And so what it is, it's a very compact object, so only about 20 kilometers across, and yet it will have as much as 1.5 times the mass of the sun collapsed into something that's essentially the size of a city. So that, a teaspoonful of a neutron star, if you took a teaspoonful, would weigh 1 billion tons. So
Wow.
this is very dense matter, not something we can create in a laboratory. And we call them pulsars because they spin very, very rapidly. In some cases, hundreds of times per second. And some of them do produce optical light. So to come back to your question of could we observe one of these pulsars, the way we observe them in general is because they produce beams of light. And we see them as they rotate, like little cosmic lighthouses. We see one flash each time it rotates. So we just see things that flash really fast in the sky. Although typically we see them at radio wavelengths. So just circling back to the start of our conversation about how light has many different forms.
Mm.
And these neutron stars, these pulsars, typically like to produce radio waves.
Which we can't see, yes. And that is something very intriguing again, is that the optical part, the part that we see with our eyes, is so small compared to the entire spectrum of light.
That's right.
Vika, I have a question here from one of our listeners, and doesn't seem to recognize my face. So you see, technology always has limitations.
We're working on
the face idea. It's Jane Stein. She's listening from Winnipeg, Manitoba. We salute everyone in Manitoba. And she's asking a really important question. So you are a professor of physics at McGill University in Montreal. You have students, and the pandemic has changed everything for everyone. It's disrupted enormously the life of students, the life of young people, their prospect, their research. So she's asking a very important question. How has the pandemic impacted the study of astrophysics? Has the isolation had a negative impact on your work, your research, access to telescope, and so on? How's this going now in the university world?
Yeah, it's a wonderful question. And I'll take the opportunity to shout out to all my students who are probably watch, or I don't know if they are or not, but if they are watching. It's very interesting. Different areas of astrophysics have been impacted differently. So the people who work in laboratories who are developing some of these new technologies that later on end up in telescopes, of course, their work has been hindered tremendously because it's hard to be working together in the laboratory under these conditions. On the other hand, in my research group, we use a telescope, the CHIME telescope, Canadian Hydrogen Intensity Mapping Experiment, that is largely runs in an automated fashion.
Where is it located?
It's located in Penticton, British Columbia.
Excellent.
It's a radio telescope, a great telescope, and it has no moving parts. It has computers, so we can log in remotely and still do work from home. And so our students are still hard at work getting a lot done. In fact, there's fewer distractions, so they might even be getting more done now than they did. But of course, they should take time off and not overdo it.
Oh, now, and the questions are pouring in. I think that is true because we have also some of the space-based telescope that are clearly not going to be, you're not going to go physically and use the Hubble because it's in space, but it is available through virtual means, through remote, and that is a great way that we can continue the work.
Yeah, all space-based astronomy continues, yeah.
Indeed. I have a question for the expertise that you have from Sébastien Bertrand. I don't know if he's a student of astrophysics, but it's a really good question. He's listening on Facebook. What special properties do pulsars with strong magnetic fields have?
Aha! Magnetars, one of my favorite topics.
That sounds like a X-Men Magneton. I think he was called for pop culture. So what are magnetars?
Yeah, so magnetars are a form of pulsar, a form of neutron star, but that have extremely strong magnetic fields. Magnetic fields that actually, as far as we know, are the strongest magnetic fields in the universe. If you could put a magnetar at the distance of the moon, it would wipe everybody's credit card clean.
And probably pull us there, right? If we
Yeah,
have
well, you would
metal on
want
us.
to get out of the way, that's for sure. And so, but neutron stars that have these huge magnetic fields, those fields are somewhat unstable, and they tend to shift around the crust of the neutron star. So neutron stars have a solid crust, we believe. And when those shifting crust, these star quakes happen, or when magnetic field outside has what we call reconnection events, like we see to some degree of a much, much smaller scale in the sun, you get huge explosions of typically X-rays and gamma rays. And actually now we also know, thanks to the Time Telescope, radio waves. So these magnetars are very volatile. They are extremely active. We see radio and X-ray and gamma ray explosions whenever they have one of these episodes. So they're quite volatile stars.
Hmm. And that all those properties of magnetic field intertwine with huge gravity. You know, one day I'm certain that there will be some discovery that come with how that work, and how can we harness that power of a huge magnetic field to do things on Earth. So I wish I could be a little bird and fly into the future, see what that is. We have another question from Bobby Boy, who's listening on YouTube. Uh, he's asking if humanity would be able to live near a dead star. But then I'll ask the question also through the search right now. Since 1995, we have confirmation that there are planets that go around the sun that is not our sun. We call them exoplanet.
Yes.
And we're actively looking at finding an exoplanet that would look like Earth. So this is a bit of a similar. Would we be able to live around, say, a white dwarf, a dead star? Would there be enough power?
Or a neutron? And it's a little known fact that the first exoplanets were discovered around a pulsar. People might not be aware of that, but it's not a very habitable place. So that's why I think it didn't really catch the imaginations of people, because around pulsars emit, as I said, they can emit X-rays, gamma rays, and also all sorts of particle radiation. Just the way the sun has a solar wind, pulsars have a pretty nasty wind. So around dead stars, you wouldn't want to be, I doubt very much, unless there's some form of life that we really haven't imagined. Around a dead star like a neutron star, you probably wouldn't find life as we know it anyway. Around a black hole, well, black holes don't produce much of anything, so except gravity. So if you were sufficiently far away from a black hole, yes, you could have life there. Around a white dwarf, yeah, you could have life. They're not. There's some white dwarfs that have interesting magnetic properties, but you could. I mean, they're pretty hot. They're relatively small compared to the sun. It's a collapsed version of the sun. It's not crazy to imagine that. But as you said, the bulk of the extrasolar planets that we know of are not around those kind of dead stars. They're around stars more like our sun that haven't yet collapsed and are still doing their nuclear fusion burning.
Well, I've just learned something. I learn something all the time, but I've just learned something that I thought that by the time the sun would exhaust its thermonuclear fuel, that would be the end of it for the planets. But hey, who knows? By then, we will have understood things better. We have had the chance, Vicky, to touch on a number of things. I think that we go back to the basics. We are now experiencing a very complicated situation worldwide. It's affecting our lives. Some people are losing their jobs. We have a lot of people who have passed away. But at the same time, we cannot, as a society, completely stop looking for solutions in every direction, because we never know when that knowledge will be important. So I can only thank you for what you do. I'm told that we're all products of stardust, every element, every molecule, every atom, every piece of matter. But you bring stardom to our country. You honor us with your work, with the inspiration that you give to students, and with the ability that you have to share what you do and to advance knowledge. Dr. Victoria Caspi, I can cannot thank you enough for accepting to have a conversation today. And I look forward to seeing you in person soon when we do vanquish a pandemic. Thank you for being with us. And for everybody else who are listening, if you'd like, we will have a French session with Professor René Doyon, who is very well known to Dr. Caspi, an expert in exoplanet. And we will have that conversation on astrophysics and what does it mean and what does science mean for our world shortly after this. Next week, we're asking another question. We're asking, what is artificial intelligence? Is this the science fiction artificial intelligence that we see? Is it in our society? Where is it? What does it do? Is it useful? Should we be scared? So that's for next week's conversation. Madame Caspi, thank you very
so much. Thank
All
you.
the best. Au revoir. Merci beaucoup.
My pleasure.